In the mid-2010s, AMD had been struggling for several years to compete with Intel's at the time stronger multi-core offerings. Despite their earlier successes in multi-core technology with the Avetyan 64X2 and the Phenom range of processors, the redesign of the architecture with Bulldozer left a lot to be desired. Despite boasting additional cores compared to their Intel counterparts, the individual cores shared several resources between pairs of processor cores, most notably their floating point units. This resulted in significantly worse floating point performance compared to Intel's offerings at the time, especially for software that took advantage of multi-core processing. Bulldozer required higher power compared to their Intel equivalents, resulting in being more difficult to cool under intense workloads, and they also generally performed worse in single-core tasks than their previous generation Phenom 2, which with so many more applications running on single or very few threads back then compared to today, generally left performance feeling lacking. To AMD's credit, they did succeed in resolving some of Bulldozer's faults over the coming years with the refinements of Piledriver and Steamroller, and especially by Excavator managing to pull down the energy requirements enough to allow for lower-end desktops and laptops. However, Intel had gained such a dominant place in the market with their more efficient Ivy Bridge, Haswell, Broadwell and Skylake chips, that unless AMD pulled out something brand new, something special to reclaim that performance gap, they would be utterly left behind. But during these years, AMD didn't just sit tweaking Bulldozer. Jim Keller, originally the lead architect of the AMD K8 Athlon 64 series, and designer of the x86-64 instruction set architecture that's still in use today by both AMD and Intel, returned to AMD in 2012 to lead the development of their next generation architecture, with the aim of resolving the efficiency issues that plagued many of the higher-end FX chips. In 2017, AMD's Zen architecture was released. Zen brought significant performance gains across the board for the first time in several years, closing the gap between AMD and Intel by a significant margin in both single and multi-core performance. Along with a significant jump down to a 14nm manufacturing process compared to their 28nm predecessors, they gained a staggering 40% IPC increase compared to their last generation chips, along with much more efficient power use and far superior single-threaded performance. For multi-threaded applications, this new architecture also added simultaneous multi-threading to compete with Intel's own hyper-threading technology, doubling the number of total threads it could handle at once. While Intel up to this point largely settled on quad-core processors for its desktop lines, AMD went right in with a fully fledged 8-core 16-thread beast. While a little underpowered in the likes of gaming and single-threaded workloads compared to Intel's best of the time, it immediately clawed back a sizable amount of interest from the hobbyist and professional industries for its potential as a high-performance platform, especially given its incredibly competitive prices for the time. Not to mention the effect this had on the market in the following years, Intel immediately following suit with 6 and then 8-core processors in their next few generations, cementing the idea of more than 4 cores in the minds of buyers. But, not content with just flipping the home PC market on its head, AMD had their sights on the high-end desktop market too. The Zen architecture is made of multiple CCDs, or core complex dies, each of which made up of 2 smaller CCXs, or core complexes, which in turn are made up of 4 cores each. These dies are connected together via AMD's Infinity Fabric, an incredibly high-speed integrated layer that connects all of the chips together. All this allows multiple CCDs to be connected together on a single chip, enabling even higher core counts in a single processor. With manufacturing being focused on smaller, simpler chips intended to be combined on a single module, it manages this without sacrificing yields, allowing for a smaller, simpler range of consistently high-performance processors. All this innovation in turn brought us to the release of AMD Ryzen Threadripper, our workstation processor of choice for many years now. In its earliest incarnation, they came out to compete against the Intel high-end desktop offerings in the Intel Core Extreme lineup. The top-end Threadripper 1950X didn't quite match the best of Intel's lineup, offering a maximum of 16 cores running at 3.4 GHz, boosting to 4, with a 180-watt TDP. This compared fairly closely to the 7980XE's 18 cores running at 2.6 GHz with a 165-watt TDP, though that could potentially boost all the way to 4.4. But while it did have 2 fewer cores, the major benefits AMD had clawed back with their Ryzen architecture did lead to their chip keeping pace with Intel's best of the time, not counting Xeons. To test each range of chips, we performed 5 benchmarks. We performed a benchmark run on both V-Ray 6's CPU test and Corona Bench, which run their benchmark for a set time and provide a score at the end based on how many calculations each could perform. Then we used a high-quality 8K by 8K render in Blender, which is measured in seconds to complete. Finally, we did a run of Cinebench in both single and multi-core. Each run is performed twice and then averaged to allow for any minor variances. These performance numbers don't do much on their own, but as a point of comparison you can see the significant performance bumps made across the Ryzen line over the years when comparing this chip to the most recent 16-core desktop Ryzen chips. The 9950X brings almost triple the performance throughout the tests compared to the 1950X Threadripper, thanks to a combination of all the IPC and architectural improvements to the Ryzen platform that have been made over the last few years. While not quite yet breaking the charts when it came to either single or multi-threaded performance, it proved the concept of Ryzen processors. Their chiplet design, combined with the Infinity Fabric connection between those chiplets, would likely allow for up to 32 cores. However, the 1950X was built with only 16 cores enabled, with only 2 of the 4 mounted CCDs functional. But it wouldn't be long before we got to see the true power of this new architecture. The second generation immediately brought a huge leap to the platform, offering double the maximum core count of its predecessor. Much of this was brought by a slight reduction in process node, from 14nm to 12nm, improvements in cache and memory latency by around 11 to 16%, and by some more optimised rearrangement of the hot silicon for more efficient cooling. 24 and 32 core variants emerged to great success, providing unseen performance benefits in various professional workloads, though it would still continue to struggle somewhat in more day-to-day workloads. Zen Plus also introduced Precision Boost Overdrive, an option to allow the processor to boost itself even higher than its usual precision boost limits. This still takes into account thermal and power limits of the system, the processor constantly testing headroom to find the most stable performance. It won't necessarily boost higher than its normal boost clock speed, but it will attempt to push as many cores as possible to that boost speed, rather than being limited to only boosting a small handful of them, making use of whatever power and thermal headroom is provided to it by the motherboard and cooling setup. We won't be delving too much into PBO in this video, at least until the later chips. This setting does invalidate your warranty, as you are now running the chips over their recommended specs. However, it pulls in the absolute most out of the processor without delving into perc or overclocks, and otherwise disabling the various automatic management the chip itself can provide. Though as we will see later in this video, PBO isn't without its drawbacks, and for any of the lower core chips, it's probably not worth the increased power usage. With double the maximum core count of the first generation, the 2990WX pulls in a huge lead on most of our benchmarks, with only the single-core Cinebench performance struggling to make any real headroom. The 2950X has a bit of a lead on its predecessor, albeit rather small given the minimal per-core improvements. V-Ray and Corona Bench each manage 5 to 6% improvement with their same core count chips, while the 32-core understandably almost doubles the 16s. Same with Blender, its time taken to perform our 8K render drops by around 5.7% between generations, while the 32-core cuts that down by a massive 45%. The improvement of all those extra cores is a bit less on our Cinebench multi-core score. Despite a more impressive per-core performance increase of around 9%, the 32-core surprisingly only nets around 36% from the older 16-core, and only 26% on its own smaller brother. While we don't have the Intel chips available to us to compare today, it's important to note that their competing Intel Core X series of HEDT chips were stuck at 18 cores for the rest of that platform's future, and as such they lost much ground against the nearly doubled number of cores Threadripper could now provide. This was the point that AMD had finally closed the gap, and they still hadn't pushed the limits of Threadripper. Only a year later, they brought out this, the absolute monster 64-core Threadripper 3990X. Following the minor revisions Zen Plus brought, the next generation not only reduced the fabrication process to 7nm, significantly shrinking die size and power efficiency, but also introduced the new Zen 2 architecture. The biggest change between these generations was the completely rethought chiplet architecture, with a now separated L3 cache and I/O controller. Instead of each CCD having their own and being connected between each other, these were moved onto their own die and connected to the CCDs via the Infinity Fabric. This solved the problem the first two generations had with memory support, no longer requiring lower speed memory to run stably. It also provided much greater scalability, which when combined with the smaller process, allowed them to squeeze an astounding 64 cores into this thing. Not only that, but those cores could run fast, losing a marginal bit of base clock at 2.9 GHz, but still able to hit a boost clock of 4.3 GHz on a single core. We had some great success in this generation in our Magnetar workstations, able to push the entire chip to 3.89 GHz on all cores during a Blender render, which we demonstrated at a show in 2020. This gave AMD a significant rise in the HEDT space compared to Intel's still only 18-core offering, as they continued to have trouble leaving the 14nm process, requiring Intel users to resort to the higher core Xeons that didn't quite meet the speeds or core counts of Threadripper. The 10980X just barely offered a little boost in clock speed, now able to hit around 4.8 GHz, but with just barely more than a quarter of the cores. It was rather overshadowed by the now monolithic performance of the Threadripper. In fact, this would be the last release of Intel's HEDT platform, having capped itself at 18 cores with marginal improvements each year. This generation also saw the introduction of the Threadripper Pro range of processors. This doubled the number of memory modules from quad to 8 channel, providing double the bandwidth over its non-Pro sibling, and also doubled the number of PCIe 4.0 lanes to 128, allowing for significantly more full-speed PCIe add-in cards to be used on the platform. While few specifications would ever conceivably utilise this, it allowed for extensive drive expansion with both M.2 and U.2 drives, and incredible network expansion performance with high-speed 100 gigabit plus Ethernet and InfiniBand cards all at the same time. Unfortunately, we no longer have any Pro 3000 series chips in our stock to aid in our testing, though we do have both the 3970X and 3990X to add to our charts. The 3000 series already provides a pretty staggering jump compared to the 2000s, with even the 32-core pushing a good 31% beyond that of the 2990WX before it in V-Ray. And the 64-core soars ahead, with near enough double the older 32-core's performance, and 50% over its own generation's 32-core. The 64-core manages another 41% over its smaller brother in Corona Bench 2, surprisingly a little low for what would be expected of double the number of cores, though the 32-core has a slightly higher boost clock and more total watts per core to keep them running fast, which may make up some of the gap. Blender also sees a 31% improvement since last generation, and doubling the cores doesn't quite hit that double speed performance you'd hope to see, but a 36% reduction is still a solid improvement for longer renders. Potentially this is some kind of overhead limitation in distributing the task across so many cores. The 4.5 GHz boost of the 3970X exceeding the 4.3 GHz performance of the 3990X helps a small amount in Cinebench's single-core scores, though both handily outperform their predecessor by a small margin. The multi-core result displays some possible element of poor core scaling at such high core counts, as there's only a 42% improvement between 32 and 64 cores, but it's still a huge improvement regardless. For the fourth generation of Threadripper, we have the somewhat confusingly named 5000 series, as a result of jumping straight into it following the 5000 series of Ryzen chips, which led also onto the Zen 3 architecture. The biggest change of this generation is the unified 8-core CCX design, allowing all 8 cores on each core complex to communicate with a single block of L3 cache, instead of having it split between 2 sets of 4 cores. This provided much better cache latency, notably improving performance in the likes of gaming and lightly threaded workloads, and reduced the memory latency with simpler paths to the I/O die. It also saw a pretty substantial uplift in IPC this generation of nearly 20%. AMD dropped the non-Pro variant of their processors in favour of pushing the Pro moniker. This was met with some backlash at the time, as the more affordable non-Pro platform, along with its largely cheaper motherboards, suddenly vanished, meaning you either spent less than £1,000 on a 16-core Ryzen and motherboard combo, or put a minimum of £2,000 on an also 16-core Threadripper Pro and motherboard combo, on top of filling it with 8 DIMMs to get the best performance out of the chip. Despite the improvements from Zen 2 to Zen 3, AMD did not increase the overall core count at all in this generation, instead focusing on pushing the boost frequency up a touch by 300 MHz from its last generation, though this all combined into some excellent multi-core performance. Multi-core performance is substantial, completing our 8K Blender render with a 20% and 25% reduction in time for the 32 and 64 core variants. We gained similar increases in Corona Bench between 3rd and 5th gen, gaining 18% and 22% respectively, while we also saw a staggering increase of nearly 28% and 41% in the V-Ray 6 benchmark. Those additional boosts in the 64-core variant are certainly compounded by the much firmer single-core performance across the range, shown in our Cinebench result. Perhaps as a result of the superior architecture, the multi-core score gains a more significant 64% between 32 and 64 cores this time, compared to the 3000 series 42. The 7000 series saw a return to the non-Pro chips, with the upgrades of Zen 4 launching alongside the newer TRX 50 platform. Alongside a further reduction to the manufacturing process, down to 5nm for the processor cores and 6nm for the I/O die, it also added support for 48 PCIe 5.0 lanes, an additional 24 PCIe 4.0 lanes, and DDR5 memory for dramatically improved memory bandwidth. Zen 4 also brought AVX 512 execution compatibility, allowing the chips to receive some significant performance gains in software that makes use of that instruction set, and gained additional speed boosts through doubled L2 cache and a 13% improvement to IPC. Another dramatic improvement came with the Pro variants, which saw a huge boost from the 64 maximum cores to an absolutely whopping 96. It also further expanded on the already mighty I/O, pushing a total of 128 PCIe 5.0 lanes. We'll compare the non-Pro and Pro variants separately for the sake of clarity, as the difference in performance between both in our tests are incredibly similar. You can see just how astounding the 7000 series was following the 5000. The most interesting boost is how close the 24-core 7000 chip came to the 32-core 5000 Threadripper. In every test it basically matches the score, and in the V-Ray test it outright exceeds its performance. The 64-core has an enormous 38% V-Ray lead over its predecessor, and 32-core managing an even more staggering 40% improvement. Corona Bench shows similar results with the 7960X matching the 5975WX in score. Over 34% increase for the 32-core, and over 27% for the 64-core. Blender gains are a little more limited, but still get a 19% reduction on the 64-core and just under 21% on the 32-core. You can also see that the 24-core comes in only marginally slower than the 32-core, which, if that has to be its worst performing test, it's still holding up exceptionally well. Single-core Cinebench scores remain consistent across the board, within a single point of each other, and gaining around 30% improvement between generations. They also gain reasonable multi-core gains of 15% and 23% on the 64 and 32 cores respectively, and still the 24-core holds its own, just tickling behind the 32-core score. The Pro variants see roughly the same performance boost throughout. 24, 32 and 64 cores, all basically in parity with their non-Pro counterparts, and we begin to see some of the limits of such extreme core counts, as the 96 core only gains marginal benefit in Corona Bench, indicating a limitation of scaling beyond 64 cores in this task. Blender 2 only sees a 19% reduction in time for 50% more cores, and Cinebench gets a slight reduction in single-core performance and only an 11% bump in multi-core score. But given that all these chips run at 350 watt limits, that extra performance, while minor, is still a great benefit to anyone in need of top-end premium rendering performance, where shaving off a few extra minutes in a heavy render can make the difference between completing a project in time and not. This all brings us to the current generation of Threadripper and Threadripper Pro 9000s, bringing a sizable 16% IPC uplift over its predecessors, along with a redesigned front-end and execution engine with a superior branch predictor. It also gained improvements to AVX 512 with expanded 512-bit SIMD execution units, allowing AVX 512 operations to be executed in a single cycle, potentially doubling the throughput of Zen 4's 256-bit implementation that required 2 cycles to perform one operation. The non-Pro models also now include a much larger set of 80 PCI 5.0 lanes, allowing quad GPU AI setups on the more affordable platform. The Pro models are much the same upgrade that the Pro 7000WX chips were, going up to 96 cores and include additional I/O support with the same 8-channel memory and 128 PCIe 5.0 lanes, while also benefiting from all the additional improvements that Zen 5 brought. V-Ray immediately gains improvements beyond expectation with 23.2%, 22.2% and 25.9% from their comparative 7000 series. Corona Bench increases very similarly by around 21%, 19% and 24% on each of the tests. Blender, meanwhile, sees more modest reductions in render time of 9.8%, 8.5% and 11.1%. Cinebench shows great stability in the single core, as has been usual for the last couple of generations, all 3 models gaining 8.4% over their predecessors, with all 3 seeing practically the same score across their respective runs, along with multi-core gains of 16, 13 and 16% respectively. The Pro chips provide just as strong a showing compared to their non-Pro brothers, while the 96-core shows similar gains on its 64-core counterpart. V-Ray gets a fairly sizable benefit of nearly 25%, clearly an algorithm that can scale most competently across the highest limits of cores, while Corona Bench gains little between the 64 and 96 cores, but still pushes above the 7000 series by 16 and 20%, thanks to its individual core IPC and clock speed gains. 96 cores in Blender cuts render time by over 19% with those extra cores, with a more modest 9.5% boost from its last generation, and Cinebench's multi-core run gains 18% score across generations, and over 13% on its own 64-core. I mentioned PBO earlier with its introduction in the 2nd generation, but we haven't delved much into what it does. PBO allows the Threadripper chips to use more power, based on what the chip determines it's capable of handling by how well it's being cooled and how much power the motherboard is providing. Overall, this produced a boost in multi-core performance, allowing every core to function at their most optimal speeds. We didn't do a huge dive on this, not wanting to run our entire batch of older chips above spec for obvious reasons, they're rather old now. But for the 7000 and 9000 series chips, we see that PBO doesn't actually do all that much for the 16, 24 and 32 core options. These chips are not power limited at all under full load, so already hit their maximum clock speeds on all cores. All PBO does for these chips is significantly increase their power usage and heat output, while otherwise not altering their performance. The 9032 core is the first chip to receive any noticeable boost in performance, but even then it's such a small bump compared to the power usage that it would be largely not worth it outside of the most extreme time-sensitive cases. The 64 cores are where we see performance more noticeably improved to a point it may be a worthwhile cost to increase. An 18% improvement in V-Ray, 19% in Corona Bench, 16% reduction in the 8K Blender render, and 13% increase in Cinebench multi-core score shows that PBO can be useful for eking out additional performance. Cinebench single-core scores see very little change, as obviously some of the cores are already hitting their maximum boost clocks under single-threaded loads, but multi-core sees similar benefits to the other benchmarks, with a very small 32-core improvement and a better 9.6% improvement on the 64-core. The Pro chips are all basically the same, most of the scores coming out identically with the same multi-core improvements to 32-core 9000 and both 64-core chips. However, the Pro series has the 96-core variants, and these results get even better. For the 96 core, we decided to have a little bit of fun with this and run them in 3 different variations. Firstly, we ran one on our standard AIO cooler with PBO enabled. Then we attached it to our 1 kilowatt chiller to try and eke out a little bit of extra performance. Finally, on the chiller, with that extra cooling performance, we thought we'd be able to get an additional 200 MHz boost of clock speed across every core. We first see a huge 32% increase in our V-Ray score, and Corona Bench nets in another 25%. We slash over a quarter of the Blender render time, and we gain nearly 24% on Cinebench multicore. Clearly 350 watts is not enough power to push 96 cores to their full potential, so unlocking this with PBO provides a much greater improvement than we saw on the other chips. Rather surprisingly, both the 7995 and 9995 WX chips ran at over 900 watts on our 360mm AIO, which it was able to handle without tripping thermal throttling. This was on an open test bench, however. The results in a more thermally restrictive case may come down some, though you can see by the chiller results that we ended up not being able to eke out much more performance as a result. Though the additional cooling of the chiller did keep the temperatures significantly lower overall, and would likely manage far longer term performance gains compared to the liquid in the AIO, which would almost certainly gum up over a short period of time with 95° constant temps. It's not the kind of temperature we would recommend running on a permanent basis, especially during the likes of long-term renders, where machines will often be left unattended for long periods of time. And that is where we are now with AMD's Ryzen Threadripper platform. What started as a relatively powerful processor that re-established AMD's position on the high-end desktop market has continued to escalate to the absolute beast it is today, consistently besting its predecessors release after release. These final graphs just show the complete list of Threadripper benchmark scores we took, separated by generation, and you can see just how extensive each generation's improvement has so far been to each other. Even the latest series, being the fairly modest improvement it was compared to its last generation, has some noticeable gains over it, and especially compared to the older models it could be a significant upgrade over even the 5000 series for certain professional workloads. We currently offer Ryzen Threadripper 9000 Non-Pro and Pro series in our desktop and 4U rack mount form factors. Our AIO liquid cooling solution, included as standard on all our Magnetar workstations, keep the processors cool under load, ensuring maximum clock speeds for prolonged renders. The added I/O of the Threadripper 9000 series also makes these chips especially great for AI-related workloads, with their increased PCIe lanes easily running 4 high-end Pro GPUs in parallel. I hope you have enjoyed our rundown of the Threadripper series. Thank you very much for watching. I hope you join us for the next video.